Hello everyone, my name is Joseph Howie. I'm from the University of Victoria, and today I'm going to be talking about our paper Scaling Up Structural Clustering to Large Probabilistic Graphs using Lyapunov Central Limit Theorem. In order to start our conversation off, we're going to first look at probabilistic graph clustering, talk about probabilistic graphs in general, and how we want to be forming clusters from these graphs. The state of the art in structural clustering of uncertain graphs is UScan, and we're going to talk about that method as that's going to be the building block for our algorithm NUScan, which is going to reduce the runtime, effectively taking the bottleneck calculation, which takes quadratic time in UScan, and reduce that down to linear time in NUScan. We're then going to validate the quality of our clustering results with some experimental analysis, and that's how we'll finish up this talk here today. So let's dive right in. Firstly, probabilistic graphs. Probabilistic graphs are much like deterministic graphs where they have nodes, the numbers in bubbles, and the edges that link them together. Now, a probabilistic graph has this mapping P, which says that each edge is going to have a value between 0 and 1, and that value is going to be the probability that the edge exists in any given possible world. So what's a possible world? Well, probabilistic graphs represent many possible worlds, which are deterministic versions of the graph that include all or none of the edges and anywhere in between. So that gets you 2 to the power of number of edges possible worlds for every probabilistic graph. And if you want to know the probability of any of them occurring, you just multiply together all the probabilities from the edges that exist times all the probabilities, 1 minus all the probabilities of the edges that aren't there. So that's how you get the probability of existence for any possible world. But we're interested in clustering these types of graphs. So we want a clustering framework which takes into account the probabilities on these edges. So there is a certain domain of clustering called structural clustering that stems back to the SCAN paper from 2006, which outlines this method for structural clustering and defines 3 types of nodes, cores, hubs, and outliers. UScan then takes that methodology and extrapolates it into the uncertain graph domain, so the probabilistic graph domain. And what it does is in the original UScan paper, or in the original SCAN paper rather, they have this idea of structural similarity, and this has evolved through many papers, and the measures they use differ from time to time, but the one that UScan picks up is Jacquard similarity, and then they define the probability of structural similarity based off of that Jacquard similarity. This calculation is the bottleneck of the whole process. UScan is able to show that this can be done in quadratic time using a dynamic programming algorithm, but we're going to find that is not going to be sufficiently fast for large graphs, and we're going to introduce our approximation, which is only going to take linear time. So probability of structural similarity, what is it? So for every single edge, E, you have this probability, and there's this other parameter epsilon because that is going to be the threshold we set on the Jacquard similarity. So you sum up all the possible worlds where that edge exists and its Jacquard similarity is greater than or equal to epsilon. So this is a naive calculation that would take exponential time, but like I said, the UScan algorithm comes up with a way to do this in quadratic time, but that's still not going to be fast enough. And just so you're clear on what this notation is, this is the closed neighborhood, or the structural neighborhood as it's called in the paper, which is just the neighbors, including the node itself. So before we move on, we're just going to look at a quick toy example based on that graph I showed you earlier. So I said you have these core nodes here, which they're like the cluster definers. There can be multiple, but in this example, there's only one. We also have 3 nodes per cluster. That's what this parameter mu is telling us. We need to have 3 nodes to form a cluster. We can toggle all these parameters. This has to be at minimum 2, and these have to be between 0 and 1. So epsilon we saw already. That was the cut on the Jacquard similarity, but eta is the cut we make on the probability of structural similarity. So we say that 2 nodes are probabilistically structurally similar if they meet this threshold requirement. Now let's talk about our approximation NUScan. So like I said a few times now, UScan is great. It gives really good quality clustering results for uncertain graphs and has been tested on real world data. However, it does not scale up to graphs that hit 10 million plus edges. It just has too much of a limitation from its quadratic runtime of that calculation for probability of structural similarity. So what can we do to combat that? So we introduce a normal distribution approximation. So we're able to come up with a way of calculating the probability of structural similarity using a special series of random variables which are going to converge to a normal distribution. How do we know that they converge to a normal distribution? Well, there is a special variant of central limit theorem called Lyapunov central limit theorem, which is going to allow us to make this assertion. So Lyapunov's central limit theorem is very much like central limit theorem from your first year statistics class. It's basically throwing away one of those conditions. So regular central limit theorem, in case you've forgotten, says that you need a sufficiently large series of independent and identically distributed random variables. If you have those two requirements, then you will get a distribution that is a normally distributed random variable when you sum that series. Now, what Lyapunov's central limit theorem says is you can still get the convergence to a normal distribution with non-identically distributed but still independent random variables, as long as there's enough of them and you meet a limit condition. The limit condition says that if a bunch of stuff taken to the limit of a very high n goes to 0, then you are going to get your normal distribution. So the details of this are left in the paper, but the understanding here is that we only need this independence. We don't need the identically distributed feature as well. And if we can show it converges through this limit, then we're going to be golden to assume it's a normally distributed random variable. So now we're going to construct our random variable to meet this requirement. So first we need to start at the edge level. So every edge, like we said at the beginning, for a probabilistic graph has a probability. So you can imagine that every edge is effectively an indicator random variable, right? You have a probability that exists, so that random variable is 1 when the probability is p, and the random variable is 0 when the probability is 1 minus p. So this gives us a bunch of random variables for each edge, specifically one random variable per edge, so you get a lot of them. And then what we're going to do is we know that the probability of structural similarity is based off the Jaccard similarity. So let's model this using our edge random variables. So we're going to construct the union and the intersection using these random variables. And then we're going to manipulate that inequality when you set it to epsilon. And we're going to get two groupings of independent random variables that are composites of these edge random variables, but they don't overlap, so we still have independence. And we're going to group those into two random variables called Z and W, which are not identically distributed, but they're still independent. Then what we do is we show the sum of these random variables converges to a normal distribution under Lyapunov's central limit theorem by checking the limit condition. And once we have that, we're ready to do our algorithm. So we define our algorithm, which runs in linear time, to say that we first check that the number of neighbors for a given node, for a given edge is sufficiently large. So in the paper, we set this to 100. Then we arrange the neighbors into our special sequence of random variables. We calculate the mean and variances for those random variables U and V, W and Z. And then we sum the means and variances to create our new random variable that's normally distributed. Finally, to get the value of probabilistic structural similarity, we then just compute the area under the curve according to the threshold epsilon that we set at the beginning. That is going to give us a linear runtime approximation for the calculation of structural similarity. In the case where the edges do not have a sufficiently large number of neighbors, we still use the DP algorithm because we won't suffer any performances if we do it for low neighborhood sets. So that's our algorithm. That's our approximation method. We're just going to plug this in when we have large enough neighborhood sets to reduce the runtime of the calculation. But how good is this approximation? So we set out a series of experiments to test our method versus the original UScan method. So what we're going to look at is direct comparisons of the cluster sets between NUScan and UScan. We're also going to look at the runtime and the scalability. We also note that in our paper, we're able to show for graphs with over 500 million edges, our algorithm is still able to complete in a reasonable amount of time, about an hour or so, whereas UScan was not able to complete within 2 days. Finally, the last bit we look at here is going to compare the cluster quality metrics of UScan and NUScan. So we're going to look at average expected density and see that they're basically identical for both algorithms. Firstly, here are the data sets that we analyze in this presentation. In the paper, there's actually 15, but here there's just 9. These data sets are real-world graphs with real probabilities or induced probabilities using obfuscation. The final 3 are actually deterministic graphs that we put different probability distributions onto, which we'll talk about later. The columns here are just showing different statistics about the graphs here. So you have the number of nodes, the number of edges, the maximum degree, the average degree, the density, and the clustering coefficient. So you can see we're going from edges or graphs with edges of 7,000 all the way to 15 million. So we have quite a diverse range of size here. we look at the direct comparison between USCAN and our framework and show that the probability of structural similarity when we calculate the root mean squared error on an edge-to-edge basis is still remarkably low. You know, it's about less than 10% for most of these graphs on this parameter point. And then not only that, we are also able to look at the cluster sets, the core sets, the hubs, and the outliers, and see that these are virtually identical between the two methods, which is great news to start off with. It's showing that we're getting very similar results. Then we look at the run times of these things to compare USCAN and NUSCAN to see if we're actually getting a performance boost. So we're looking at those three larger graphs in the data set, Enron, CNR 2000, UK 2014, and we're looking at three different probability distributions. So we induced an exponential distribution with a mean of 2, we induced a normal distribution such that it fell between 0 and 1, and then we also put on a uniform distribution giving values between 0 and 1. With this, we can see that as we go to the larger and larger graphs, USCAN becomes a lot slower compared to NUSCAN. And then when we go into more normal distributions, so if we go into the normal and uniform distribution, we actually see this start to take off even more so. So this bar and this bar are capped at 2 days because we did not allow any of the algorithms to run for more than 2 days. So these did not actually complete. So when we compare this, it's looking like our algorithm took about an hour, actually a little bit less than an hour, whereas USCAN is taking over 2 days. And when we go back to our direct comparisons, we're seeing that we're getting very similar results. So that's good news. So this is for the data point, or for the parameter point rather, 0.8, 0.5, and 2. And we're seeing that we're getting very good results here. One of the things to note is in the both algorithms, there is a threshold cut or a pruning step called eta pruning, which takes into account that there is this mathematical notion where if your edge probability is already less than eta, then the probability of structural similarity is not going to become greater than eta. So we do not have to even bother doing the calculation, as we know from the fact that the edge probability is already lower. Then we finally move on to comparing the cluster quality. So we're looking at cluster quality on now this parameter point here, and we're able to see that USCAN and NUSCAN have basically the exact same average expected density over the course of varying eta and epsilon on the different runs here, which is very impressive when we look down to the actual data point of each of these plot points on the chart. We'll see that the numbers actually agree up into the 10,000th decimal place. So these are virtually the same clustering results when we compare it at this aggregate level and when we compare it at the individual node level, looking at the cluster sets. So just to summarize, USCAN is the state-of-the-art in clustering probabilistic graphs, and in their original paper, they compare it against some ground truth data sets and show that they get very strong results. However, it does have this very noticeable bottleneck when you scale up to large graphs where it will not complete because of this quadratic runtime of the probability of structural similarity. So with our algorithm and USCAN, we're able to improve the runtime and subsequently the scalability without sacrificing any cluster quality results, as we have shown. Our algorithm is also able to scale up to graphs with over 500 million edges and still complete in about an hour. And we're able to show that the results are virtually indistinguishable. So we're getting pretty much the same clustering results that you would get from USCAN with NUSCAN, which is exactly what you want when you're approximating the algorithm. So thank you so much for listening to my talk today.